Hello again. So let's solve this problem, which is the same one that I solved before using the method of the portal, but now it's going to be an approximate method called cantilever. It's exactly the same problem. All the areas of the columns here are the same. So the area of the column A, B, C, or D is the same, and we're going to be call it A. The first step is find the centroid. But the centroid of the areas of the columns. How do we do that? It's just a weighted average of the columns. So if we are here at A, for example, we're gonna say, I'm gonna do it like if I don't know. Of course, in this case, I know it's gonna be at the center because everything is symmetric. But let's say that it's not symmetric. So I'm gonna do it like assuming that the values of the columns are different of the areas, and the distances also are different and they are not symmetric. So basically you can do this and you can say the summation of, I don't know, you call it moment, but let's say summation of weighted average, aka moment. I'm gonna put it like that. Moments at A equals 0. Remember, this is not a moment, but I'm gonna say it like that. So basically what I'm going to do is I'm going to take the area of the column B multiplied by 8 plus the area of the column C multiplied by 14 plus the area of the column D multiplied by 22 divided by area A plus area, the total area B plus the area C plus the area D. I don't know what I call it moment. You could have said also that centroid is just the summation of A times distance divided by the summation of the areas. It's the same thing. Or xi here, or xi is the same thing. So in our case, all the areas are the same. So this is A, and A. I can take it out of the equation. And this is 4 times A because it's the same. So x bar is going to be A multiplied by 8 plus 14 plus 22 divided by 4A. These and these cancel out. And then you have 44 divided by 4, which is 11 meters. And 11 meters is exactly what we said was going to be at the center. If everything is symmetric, it's going to be at the center. But now at least you know what to do if it's not symmetric. That's the first step. Second step, it will be place hinges wherever the hinges need to be placed. And that has to do with the form shape, remember, and the deflected shape. And for these cases, because everything is symmetric, we need everything is symmetric now because everything is fixed. We need to add hinges at the center line of columns and at the center line of beams in order to make it statically determinate. Okay, now we have that part. Hinges are placed. Now we proceed to calculate whatever we don't know. This centroid, if this is the load that is applied in this direction, and I consider the whole thing as a cantilever, once these start moving in this way, these columns are going to have to keep it into place, like that, and this is going to be pushing in that way, with the central point at the centroid being the 0 line. And remember, these are stresses. This is the other thing that you have to really pay attention. This is related as stresses, stresses. And that's the way we're going to calculate the value of the forces. Here, 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 and here. So how do we do that part? Now we can do summation of moments at this part, let's say. I'm going to do that, but I'm going to make the cut at this point. So this diagram, I'm going to copy it again. It's going to be referred to this one because it's going to change. But you know that this is the general one. So I'm going to just reproduce this here this part here, like that, with the cut made at this point. When this distance is 2, and we have this 20 kilonewton force here. And once again, if we have this part, basically what we are, I'm gonna revert this to make it simpler, like that. And then we have this situation like that. Now, if we have this is gonna be the stress IE, or stress EI, stress JF, stress here KG, and this here is going to be a stress LH. And now we can see that between these stresses there is a linear relation. And I'm focusing on stresses just because you need to know that if the areas are different, you need to compare stresses. And axial stresses is the force divided by the area. In this case, because all the areas are the same, these and these are going to be the same also. I'm going to be referring to forces or stresses independently. However, keep in mind that if the areas change, you are comparing stresses and not forces. Okay, so what do we do here? I can say summation of moments at, I don't know, anywhere. What is easier to do here? We can do summation of moments at here at this point. Let's do at that point. Let's call that point M N O P. So let's do summation of moments at M, summation of moments at M equals 0, like that, in this part. So M is this value here. Now, if this is the correct distribution, I'm going to have this force here, this force here, this force here, and that force over there. The distances are given. This is A. So if you do moment here, the first thing you're going to have is 20 times 2, negative 20 times 2. And then you have this part here. What is this part here? This part here is going to be FG, or GF, or FG, and this is going to be KG. So it's going to be FG, negative FG multiplied by this distance, which is 8, and then plus everything from this side to this side of the centroid is going to be acting downward for this case, and everything to the right of the centroid is going to be acting upward. So it's going to be plus kg times the total distance, which is 8 plus 6, 14, and then you have this other part here, which is LH multiplied by 8, 16, 22, and that has to be equal to 0. And what can we do with this, because we don't have anything that is the same thing? Well, we don't and we do, because now we have the relation. You can relate you can see the distances now. What are the distances? These distances are given, as I said. This is 8 meters, 6 meters, and 8 meters. And that means that this is 3, and this is 3. And that means that JF is going to be equal, different signs, but it's going to be equal to KG, because there is a ratio here. And then if you have that, we can also calculate LH, and we can calculate LH in terms of kg, which is the same JF. So if I say, for example, that LH divided by this distance, how much is that distance? 8 plus 3 is as 11, as kg is as 3, then we can calculate kg instead, or LH in terms of kg. So I can say that LH is 11 divided by 3 kg, which is also 11 divided by 3 JF. And now we can put everything in this equation here. So I can say negative 20 times 2 minus FG, I'm gonna keep it like that, plus kg, but kg is FG or GF, same thing, JF, I'm sorry, JF times 14, and then you have LH here, but LH is 11 over 3 JF times 22, and that has to be equal to 0. And from here I can calculate JF. So JF is going to be equal to calculator. So JF is going to be equal to, I don't know, a bunch of things. Let me see. 11 times 22 divided by 3, 14. Mm-hmm. 0.462. Let me keep it here, kilonewton. So that's the value for JF, which is the same value for kg. And if I want the value for LH now, LH is going to be equal, by the way, LH is going to be equal to EI for same reason, because of symmetry, and that's going to be equal to 11 divided by 3 multiplied by that, and that's 1.69 kilonewton. Now we have all of these forces here, acting here, 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 here. What is the next step? The next step is now proceed and make a cut there. So we're gonna do that. We're gonna make a cut there, and if we do that, what is the difference? The difference is, well, there are several differences. I'm not going to put the hinges, but remember, all of the hinges are placed here, and this is also a hinge. This is important for me to put. So this distance here is 4, and this distance here is, if this is 6, this is going to be half of 6, which is going to be 3, and then this force here was 20, and this force here was 40. And then we proceed the same thing. The centroid is here. Now keep in mind something. All the columns are the same, but if the top columns are one dimension and the bottom columns are different dimension, and they change with respect to each other, the centroid of the top part could be different than the centroid of the bottom part. So the relationship of the stresses is going to be also different. It's not going to be symmetric like that. So then you have this, and we can call this part, I don't know, N, that point over there, just for saying something. And this is called AE and BF and CG and DH. Once again, these forces are applied like that, meaning if you do the your forces, this is gonna be like this, like that, and like that. And when you do the distribution also, then you're gonna have a similar thing that we got before. This is like that, pass it through the centroid, and to this value. This is AE, this is DH, and these two are the same. I mean, the drawing should be better, but you know, everything is symmetric. And because everything is symmetric, we are basically repeating what we did before. This is 5, this is this is 8. 8, this is 3, this is 3, and this is 8. And if you do the ratios between these, you're going to get exactly the same ratios that we got before. AE, the stress, I'm going to reinforce this, the stress at AE has to be equal to the stress DH, the stress BF has to be equal to the stress CG, and this one we can do the same thing. The stress DH divided by 11 has to be equal to the stress CG, which is going to give us the stress at DH is going to be equal to 11 over 3 times the stress of CG. And then you have here these relationships. These are the real relationships that you have to use. Now remember, if the areas, I'm insisting in this because there is a bunch of problems that the areas are not the same. So if the areas are not the same, then this equation will be the force of the column AE, which is what we are looking for, divided by the area at AE has to be equal to the force DH divided by the area DH. And from here, you know the area, so you can solve for the forces. And same thing repeats with all of them. In our cases, because area is constant, then all the stresses, relations, and everything is going to be related directly to areas. So I can change that equation and put areas. So what we are doing here is doing summation of moments about the point N equals 0, like that. Then you are going to have 20, negative 20 times 7, negative 20 times 7, minus 40 times 3, minus BF times 8, plus CG times 8, 14, plus, is it plus? Plus, yes, plus DH times 22. I'm solving this problem as I'm working with you, so that's why I'm hesitating sometimes. Equals 0. Now we have also these relations here, and we can put everything as we did before. We can call this BF. This is BF, right? If we do moment and N, which is what we are doing, now this is BF. BF and CG are the same. So I can put here BF and I can put here BF because they are the same. And when I go to this one, I can say that this is 11 over 3 BF because this is also 11 over 3 BF here. And then I can solve for BF. When I solve for BF, then you're getting that BF is equal to 3 kilonewton, which is also the same as CG. CG. And DH is going to be 11 over 3 multiplied by that, meaning this is going to be 11, and this is going to be equal to AE. And now we have the extra piece of information that we needed. So now we know the values of the internal forces and the columns. What is the next step? Now I'm going to take advantage of the hinges. I'm going to make these cuts everywhere where the hinges is, when you have hinges, and when we do that, we are going to end up with this. There you go, like that. I'm just missing some values here that I'm going to put immediately, because we already know those values. What values do we know with respect to that? Okay, we know, for example, when we calculated this, we know this value, EI, and EI is 1.69. So I know that, and I know this value also, and that value was 0.46. So I can put that, I can put these values that we already know, 1.69, which is the same value here, 1.69, and then I can put here the other value was 0.46, also down, sorry, 0.46, and then in this end, I'm just copying from here, so this is kg, and kg, where are you? Kg is here, the same value as JF, which is 0.46. So this is going to be now in this direction 0.46, and this is going to be 1.69. All of those values we know, and we know this part also. We can start putting them, because this is 0.46, 0.46 in the other direction, 1.69. And we also know these values here. The values for the columns are 11 here and here, and 3 here and here. So I know those values, so we can put those values here also. 11, 3, 3, and 11, and transmit those values, or transfer those values to the bottom columns, and here 11. So once we know that, and we have those values in place, and we know those are hinges, then basically we are set up to start solving this. I'm gonna call this, I don't know, 1, and if we focus on 1 in this part, I know that at this end, this particular end, we're gonna have 2 forces, because those are hinges. I'm gonna have 2 forces. I'm gonna have one force in this direction, which it comes also. So if you study from 1, you can say from 1 you can say summation of forces in y equals 0. So if you say summation of forces in y equals 0, then what do we have? We have 1.69 in this direction, meaning this one is going to be 1.69. And if we do summation of forces in x equals 0, well, I don't have this one here, so this equation I cannot use immediately. But if I say summation of moments at EI, remember we have one force here, and we have one force here also in this part. So if I say that, and I say summation of forces at summation of moments at EI, I'm gonna have a force here, which is the force IJ. So if I do that here, this distance is 2. So you're going to have negative 20 times 2, negative 20 times 2, plus 169, plus 169 times this distance. That distance is 4 times 4 minus ij times 4, that has to be equal to 0, and then I can calculate for ij. Ij is going to be, not to be, that is the question, 1.69 times 4 divided by, you see, summation of moments here, so you have negative, positive, positive, negative 20 times 2, negative 20 times 2, that's correct, negative 20 times 2, and then I have 1.69 ij times 2, ij times 2, ij, where is ij? Ij times 2, not times 4, times 2, times 2. Ay, 40 minus 1.69 times 4 divided by 2, that's 16. ij is 16.62. 16.62 in the same direction, so that assumption was correct. Now we can do summation of forces in x equals 0. If I do summation of forces in x equals 0 here, I can find this other force, which is going to be 20 minus 20 minus 16.62. That's the only thing that I have, and that's 3.38. So now I have that 3.38. There you go, and ij is 16.62. Now we can transfer this here, so 16.62, and also I can transfer this one here, 1.69, which is this one here. What else? And I'm going to have these values here. I'm going to have these force, and I'm going to have these force, which I don't know them yet, and I'm going to have that force over there, which I don't know them yet. So how do we find that? Well, let's call that 2. Let's call this section 2. Now, if I work with that, with section 2, let me see what can I get. Oh, I can do summation of forces in y equals 0. And if I do summation of forces in y equals 0, I'm going to have 1.69 coming down, and 0.46 coming down is going to give me that value over there. So 1.69 plus 0.46, that value is going to be 2.15, 2.15, which is going to be here, 2.15, pointing up. And what else? I know that value now. What if I do summation of moments at this point? What point is that? I have no idea what point is that. That point is called, I call it n here. So I can call it n. Summation of moments at n equals 0 in order to calculate this force here. So summation of moments at n equals 0. If you do moment here at n, then you have ij, but I know ij is 16.62 in this direction, negative, negative multiplied by this height, and that height is 2, plus 1.69 times this distance. How much is that distance? That distance is this distance, so it should be half of 8, 4, 4, and then you have plus 215 times 4 minus jk times 2 equals 0, and then we can solve for jk. 16.62 times 2 plus 1.69 times 4 plus 2.15 times 4, and everything is going to be divided by 2, 2, 2 by 2, 2. Let's see again. 2. Oh, I mess up in the calculations again. 16.62. 16.62. Where's my 16? This is live, guys, so I'm messing up. I'm not editing anything. 16.62. This one times 2 negative plus 1.69. 1.69 times 4. 1.69 times 4. That's correct. Then you have 2.15. 2.15 times 4. Why did I say 4? This is not 4. Oh, this is 3. Look at that. And the same thing can happen to you. That distance is 3. So this is going to be times 3. And this one here, yes, is going to be times 2. So let's check this out. Negative 16.62 times 2 plus 1.69 times 4 plus 2.15 times 3 divided, pass this to the other side, divided by 2. That's going to be 10.0, 10.0, and I don't know even why I put this negative because it's supposed to be positive. So it's going to be 10.01. That's the value for that one there. 10.01. 10.01, meaning this is 10.01. And this one in this direction is going to be also 10.01. And this one in this direction is going to be 2.15. And anything else that I know from here? Well, I could calculate this one. This one is going to be going up, and it's going to be this minus this. 2.15 minus 0.46. That's going to be 1.69, which we should know beforehand. But anyway, 1.69, which is going to be transferred here as 1.69 also. You see? That's what I say, that we should know it anyway, because if you look at this side, you should know how much is that one there. So then we can do the same thing. We can do summation of moments at that point. At that point, we call it before O. So I'm going to call this 3. And in 3, if we go to 3, we can come and we can say now, okay, summation of what at what? Summation of forces in Y, we already did it. Summation of forces in Y, we already did it. Now I can do summation of moments at this point. We can do that. Summation of moments at this point. And summation of moments at the point O. Summation of moments at O equals 0. We're going to put this force here, which is called KL. So if we do that, we're going to have, I'm tired. This is going to be 10.01 negative times the height, which is 2. Now plus 2.15. I'm not going to fall for that again. This distance is 3. Now plus 1.69 times half of that distance. Half of that distance is 4. Plus FL multiplied by this distance, which is 2. And then we can solve for, and that 0. So we can solve for FL, and FL is going to be 10.01 times 2 plus 2.15 times 3 plus 1.69 times 4. And that has to be divided by 2. And then we have 3.4. 3.4. That's our value for FL. 3.4. 3.4. Okay. Now what else? What else? This value here is, what do you call it? You see what happened? I don't even understand my own penmanship. KL. And then somebody say, oh, would you mean KL? Yes, that's what I meant, KL. 3.4, which is the same value here, 3.4, which is the same value here, 3.4, which now we can calculate the value here because this is 10.01 and this is 3.4. We can do summation of forces in X, and I'm going to need an extra force going in this way, which is going to be 10.01 minus 3.4, 10.01 minus 3.4, and that's 6.61. 6.61. There you go. Now we are basically done at the top level. Now we transfer the forces to this part, and we keep going. So let's call this part 4. That was this one. I just did it. Now let's do this part and let's call it 5. So if we do 5, remember this 3.38 is going to be transferred here. I didn't put it before because I didn't know anything about the value. This is 11. Summation of forces in Y. If you go to 5, you don't have to copy this every time, but if you go to 5 and you say summation of forces in Y equals 0, okay, what do you have? You have negative 11 plus 1.69 plus whatever that value is. And that value is, I don't know, the shear vertical EF. The vertical EF equals 0. You don't have to copy this. You can come directly here and you can say, oh, this value is 11.11 minus 1.69. Is there any other value that I have? I don't have any other value that I know of, so this value is 9.31. 9.31 right there. And now we do the same thing. We can do summation of moments. Where do you do moment? Well, you can do moment here, you can do moment here. If you do moment here, it looks convenient. Let's do moment at E. Summation of moments at E equals 0. When I say it looks convenient, it's just because I'm eliminating a bunch of equations if I do that. So if I do moment at E, this distance here is 4. This distance here is 2. This distance here is 3. And this distance here is 4. 4. So then I can put my force that I want to calculate, and I'm going to call that force EF. EF. So if we do that and we do moment at, what I say, E, and I'm going to have to calculate this force, of course, here, and that force I'm going to call it EA. So if I do moment here, we're going to have 3.38 multiplied by 2 plus 9.31 multiplied by 4. This passes through the point. This one minus EA multiplied by 3 equals 0. If we do that, then we can calculate that value, 3.38 times 2 plus 9.31 times 4 divided by 3. That's 10.16. 10.16. Remember, all the units are kilonewtons. I'm just not copying all of them because it's gonna be a pain. 10.16, and immediately once you know that, you put it here, 10.16, and you already have this, look, 10.16, and you have this, which is 11, and now you can calculate the moment at the base of the column because you know this part. How much is this distance? This distance is 3. Meaning, if you do moment here, that moment over there is going to be equal to 10.16 times 3. 10.16 times 3, and that's 30.48. There you go. We have the 3 reactions now at this part. Now we can keep moving. Now we're here, right? So I can calculate this EF by just doing summation of forces in X. 40 going in this way, 40 going in this way. So I have 40 minus 10.16, this 10.16, plus 3.38, and I'm going to get this value, which is 33.22. At the same time, I got this one, which is the same, and then I get this one, 9.31, and then here, remember, we calculated that value over there. That value over there was 6.61, which is going to be the same value here, 6.61. And now we proceed to calculate whatever we need. We need this value here. This is 9.31 going down, 0.46 going up, 3 going down. So that means that this value here has to go up. How much is this value? That value is going to be negative 9.31 minus 3 plus 0.46 is 11.85 going up because it has to be opposite to whatever I was doing here. 11.85. And now we can do the same thing, summation of moments. If you call this here, I don't know, 6. You can call this here 6 if you want to. And then you can come here to 6 and do summation of moments here. Then you can calculate this force here, and then doing summation of forces you can calculate the other one. I'm just gonna copy the values for you to have. This is a problem that is solved in the book. Not in the book, I'm sorry. It's proposed by the book. And from now on it's just repetitive, whatever you have to do. So you can go and practice on your own, that part at least. Otherwise this video is gonna be forever and ever. And remember, there's a bunch of these values that we already have from before, like here. It's just a matter of copying the values that we have and transfer the values. Now you want to calculate this, you have that. You basically can calculate this just by adding them up. 10.2, right? 10.1, 10.1, 10.1 here. And what else? And then here the same thing. You have 10.1 in this direction, and if this is 10.1 and this is 3, you can calculate the moment, and the moment is going to be 30.48, which is the same thing that we got here, because this wasn't 10.1, this was 10.16, but I'm just not taking into account the rounding errors. So at the end, this is going to be a moment of 31, not 30.48. And then you can transfer these forces here also. 19.85, which is going to be the same thing, 19.85. And you transfer that, 3, 19.85. Summation of moments here. This is going to be 3 times this, because this is 3. 59.55 and this is gonna be the same because it's symmetric. And I don't know if I'm missing any value somewhere, but if I'm missing any value somewhere, you can do it. Now once you have this, you can go and draw your shear moment diagrams and finish. Now this problem, I presented it in another video, which is interesting. I wasn't planning even on commenting onto that, but I think I saw the papers somewhere here in my mess. Yes, you see, this is the same problem that I just did, and this table is a table that I prepared. I use software in order to solve the correct values of the reactions and the columns. In this case, these are the moments at the columns. This is the correct value of the software. The portal method was giving me 30. The cantilever method was giving me 30.48. It's about 39% of error. For the interior columns though, look at the values. Portal method, 11% error. This one here, 59.55 versus 60. Is almost to the dot over there. Now, the shear, 28% for the portal method, 27% for the cantilever method. For the shear for exterior, the shear for interior columns, the error was, the correct software value was 16.24. The portal method that we solved before in the example gave me 20, and the cantilever gave me 19.83, 20% error. Axial, portal method 13% error, cantilever method 15.5% error. And this is the axial for exterior columns, and the axial for interior columns 12.8 and 27.5% error. As you can see, I mean, the errors are there, but they're not that much. 20% error for having something that allows you to take a quick look is not that much. Of course, we will strive for getting the best results, and for that you have software and you can use software. So I see you next time, guys.